when you see a wave that looks like a slinky, like this one, that's called a longitudinal wave. Tudinal. Wow. So we have these two types of wave. We have longitudinal and transverse waves. And longitudinals look like this, and then transverse waves are that typical, like kind of up and down thing that you might be used to seeing. And then we also have mechanical waves, which are waves that require a medium, and then non-mechanical waves. And so you can have a longitudinal wave that is a mechanical wave, and you can also have a longitudinal wave that is not a mechanical wave. Same thing with transverse. You can have a transverse wave that is mechanical, and you can have a transverse wave that's not mechanical. So just because you have a longitudinal wave, that doesn't mean that it can't be that it can't require a medium and or a mechanical wave. And just because you have a transverse wave, that doesn't mean that that definitely is not a mechanical wave. So that mechanical term is not and longitudinal and transverse are not mutually exclusive. Now you can't have a longitudinal wave that is also a transverse wave. That won't make any sense because the longitudinal wave is about how it looks, not whether it requires a medium or not. So that's kind of an important point. And then for these longitudinal waves, we label different parts of it. So you can see right here, the wave is kind of squished up. And then also right here, the wave is kind of squished up. So those are the compressions. Okay. And I like to think the wave is compressed, right? Compressed means something is squished up. If you buy a compression sleeve or you buy like Under Armour compression wear, right? It's tight. It squishes you, right? It squishes you up. So that's compression. A rarefaction are these spread out parts. Okay. And the way I like to think of it, if you think of the particles of the wave as being these little bits of slinky, right? The bits of slinky are more rare, right? Or less common, like that type of rare. So that's how I remember the rarefaction. You can also remember the rarefaction because it's the one that's not a compression, since there's only two terms for a longitudinal wave. So on your test or your quiz, it might ask something like, what is part A on the wave, or what is part B on the wave, or something like that. And then if you wanted to do a wavelength on this wave, it's from a wavelength, by definition, is from one part of the wave to the same part on the wave again. So if we wanted to do a wavelength here, if we started at the front of this compression, the wavelength would go to the front of the next compression. And this is our little symbol for wavelength. Okay, if we started here at the back of our compression, then our wavelength would go all the way to the back of this compression, right? So the wavelength is from the same part, from one same part to one same part. So if you start at the front of the compression, it goes to the end of the compression. So this wave right here, we've got this one, and then we've got one more, right? So this picture has two wavelengths in it. So that's a little more than I was going to go into, but I think it'll be helpful. Let's look at the next slide. Can you see this? Let's see. Okay. So this is a transverse wave. So transverse waves kind of look like mountains, where a longitudinal wave looks more like a slinky. I cannot get myself to write a V. There we go. Okay. And so then we can label different parts on this transverse wave. I'm going to start actually with the rest position. So the middle of your wave, which is like equidistant from the crest and the trough, which we'll get to, is called the rest position. And this really should be a flat line, but I'm not very good at it, at drawing perfectly straight lines freehand. So this is what we call our rest position. Sometimes they call it the equilibrium position. think they say that in the video, equilibrium. Okay. And then, so that's that rest position. Okay. Now the crest is the very tippy top of the wave. Okay, so both of these are crests. Okay, it's just your top of your wave. Okay. Then if you wanted to do your trough is going to be the very bottoms of your waves. So if you think of your wave as a mountain, the top of the mountain is the crest and the bottom is the trough. It's such a weird word. And then this one we can also do, we can say how many waves are there. So in this one, so your wavelength is from one point on the wave to the same point on the wave. So for this one, since we have the crest, if we go from crest to crest, that would be one wavelength. Okay, then I'm going to go from crest to crest again. That's another wavelength. I'm going to do it one more time. And I'm going to go from crest to crest one more time. And that's another one. And then we have this little bit out here, right, which is like half of the wave. So they'll call this, I think they call this like 3.5. And again, this picture is from your test. I'm not going to reinvent the wheel and try and make up my own pictures. So they might not ask you all of these things about this picture on your test, but you know, it gives you an idea of it's a good transverse wave. So let's talk about waves hitting boundaries. So if you can think about like waves in a pool, right? If this is a pool and like let's say you threw a rock in, okay, your rock's gonna go and you're gonna get these like things like this, right, getting bigger and bigger, and then when they hit, then it's gonna bounce back and keep going back, right? So when a wave hits a boundary, whatever it is, when it hits that boundary, it's gonna bounce back and then travel along there. Okay, so like we used to do this lab with my students with slinkies. So we would have a student here, and we'd have a student here. We had these huge slinkies, springs, I guess. And we'd have it, and then we'd have one person hold it still, and the other person would like flick their arm to make this bounce, right? So then we'd have this wave going like this, and when it hit this kid, the kid would feel it, and then the slinky, that energy would travel back over here, hit this kid, travel back over here until it, you know, slowly getting lighter and lighter and lighter until it, you know, just kind of died out. So when waves hit boundaries, this is energy, right? So the energy is hitting this wall. It's going this way, it's going to hit the wall, go back this way. It's going to come back smaller and smaller. So like if this was our wave the first time, then the next time it might be like this, and then, you know, like this, and then eventually it would just be flat. Okay. So when waves hit boundaries or they hit something, they're gonna bounce back until they run out of energy. So this is a picture from your test. I really don't like this picture. It bothers my eyes. See, I feel like it's moving. It looks like it's moving to me. I just the more I see it, the more I don't like it. But basically what they've got is they've got you know, two kind of bullseyes and they're like overlapping each other. And so that's kind of what you're seeing. And so this is called interference. I don't think it's a great example of interference. I mean, I just, so it's kind of confusing, and so I wanted to just go ahead and show you guys that. I'm gonna go away from that page because I don't like it. Now let's say that we've got a wave, and we've got we have one student over here. They're sending a wave pulse this way, right? And then we have another student over here, and they're sending a wave pulse on the slinky this way. Okay. When these two waves meet, Okay, because they're both, if you think about it, on top waves, if this was the rest position, right? Both waves are um like on top waves, if that makes sense. They're going to add together. So you're going to have this plus this, and they're going to get, if this would say like 1 unit tall and this was like 2 units tall, then this would be like 3 units tall, if that made sense. So they call this constructive interference because they add together. Okay. So this is a way you can get something to be louder or get harmonics that kind of, anyway, um, like kind of like the bridge example they were talking about in the video. So we've got, if they're constructive, they're going to add together. This next page, we'll do destructive. Okay, now if they're destructive, they're going to subtract. Okay. Okay, so let's say we've got one student is sending a wave pulse this way, another student is sending a wave pulse this way on the slinky. When these two meet, right, one's above, so they do kind of, I guess, add together, but it's kind of like this one's a negative. So if this was like 1, say it was like 1 unit tall, and this one was like -1 unit tall, then, you'd get just like a flat line. And this is destructive interference. So constructive interference, they add up to make the wave more powerful than it was in the first place, than either of the other ones. And then in destructive interference, they add together um, to make something that is less powerful or smaller than either of the two initial waves. Um, so now this is this is one of our formulas. It's in the videos. We'll talk a lot more about this when we get to sound, but they discuss it a little bit here. I always called these harmonics, but some people call them overtones. I think the video and the test call them overtones. You can call them resonances, like where will it resonate. Like for example, like when I would study instruments with my students, we would talk about like the first harmonic or the second harmonic. That's what these are. Okay. And what they are for right now is the first harmonic is just whatever your frequency is. The second harmonic is 2 times that frequency. The third is 3 times that frequency. The fourth is 4 times, and the fifth is 5 times. Now, when we get to open and close pipes, you'll see that some of them they work a little differently. But on your test, right, they could ask you. So if your F is 500 hertz, right, and they could ask you, what is F10, right, or the fifth harmonic, or the fifth overtone, or the fifth resonance, or whatever they want to call it. So if this is 500 hertz, then your second frequency would be 2 times 500, which is 1,000, right? They could do 3 times F. And actually, one of these is the one they ask you in the test. I just did a bunch of different ones, so I wouldn't be giving the answer away exactly. I'm just going to draw a new 3. 3 times 500. Right, so that's going to be 1,500. If this was a short answer, you'd want to show this work part, even though it's simple. You'd want to show it. And there's a couple reasons, by the way, that we want you to show your work. One is because then we know that you know how to do it. But two, if you don't know how to do it, it's easier for me to see where you went wrong and to help you and to help you fix it. Like, because sometimes I can tell that you might have just forgotten a parentheses, or your work is all right, but instead of 1,000, you just wrote 100. Well, you just forgot to write that last zero, right? That doesn't mean you don't know what you're doing. But if you had just written 100, then I would have gone, was she dividing by two? Was she dividing by 500? How was she getting this, right? How is she getting this 100? Where if you did 2 times 500 and then you wrote 100, I'd go, oh, okay, he or she just wrote the wrong thing. So that's why if you guys will notice on your classwork, on your assignments, if you get the wrong answer but you show your work, I go ahead and I give you full points for showing your work, even though technically your work wasn't the right work. And that's because by training you or teaching you to show your work, and giving you credit for showing your work even if your answer wasn't right, you guys get in the habit of showing your work, and then if your answer's not right or you did something wrong, it's easier for me to tell what you did wrong. Because if you don't show your work, I have no idea where you went wrong. There are a million ways to mess up, right? And so by showing your work, it shows me what you did wrong and how we can fix it. So I'm not just trying to be like a total jerk. It actually helps you out, because if I didn't give you credit for showing your work, then if you got the wrong answer, then you'd get like 0 points instead of at least just a few. So these are how we do our harmonics. Okay, like this: 1,000, 1,500, 2,000, 2,500. And it's just, if we wanted to do, if they said like, what is F20, right? You could do F20. You could do 20 times 500. Okay. They're not going to ask you F20, but they could, right? And you'd know how to do that, because it's just, whatever this little number is down here, that's what you multiply your initial frequency by. They could also do something where they say like F5 is equal to 2,500. What is F1, right? They could do that, and it wouldn't be terrible, because F5 equals basically 5 times F1. So we could just divide 2,500 by 5 and get, 500. So they could ask you a question like that too, and that's totally fine. You can do it. So those are those frequency ones. And again, we'll get way more into this when we get to sound. This is just kind of a cursory overview. When I taught this in the face-to-face classroom, I actually put this